Fourier ptychography is a technique that measures a sample at various illuminations and then stitches together their frequency spectrums to recover phase and achieve a high space bandwidth product image. It's often applied for super resolution in biomedical fields or for satellite imaging. While traditional Fourier ptychography can be very useful, it suffers from expensive data capture and requires spatial translation along two different axes. We introduce a framework to use a slit aperture for Fourier ptychography. We only translate along the axis corresponding to the short end of the slit. This allows us to achieve similar results to traditional reconstruction with less measurements and only one axis of translation. Our method also supports rotation of the slit around its center for similar gains while trading off frequency coverage for ease of data collection. We present experimental results of both translation and rotation in simulation and on an optical breadboard setup. Stop by our poster to learn more.
Diffusion inverse solvers use pre-trained diffusion models to solve inverse problems without any fine-tuning. While they perform well on standard image tasks, these benchmarks usually rely on an exactly known forward model. We propose using Lenses imaging as a challenging benchmark because its forward model is highly ill-posed, ill-conditioned, and subject to mismatch in practice. We evaluate these solvers on real lensless measurements. Diffusion solvers slightly outperform untrained methods, but unsurprisingly do not outperform direct supervision. Importantly, they are not robust to model mismatch. The performance degrades as forward model correlation decreases, while gain errors change the strength of the data constraint altogether. On synthetic measurements, diffusion solvers are robust to added noise, and they're most helpful at moderate noise levels where measurements sufficiently constrain the solution. Overall, diffusion solvers are a promising regularizer when large amounts of data are not available, but real-world use requires more robustness to model mismatch.
To capture clear images, engineers stack complex optical elements to correct aberrations, making camera lenses bulky. Biology evolves differently by keeping the optical system simple. Although the sharp vision is limited to a small region called the fovea, the eyeball moves dynamically to redirect the scene. Adapting this biological strategy, we propose the fovea camera using a dynamic deformable faceplate (DPP). By optimizing DPP deformations through differentiable optics, off-axis aberrations are corrected locally, producing a foveated image with enhanced sharpness at the fixation point. Stacking them yields an aberration-free composite image. We compare the fusion result of the fovea stacking and the single static capture, and also apply it to the extended depth of field imaging. Moreover, with fovea tracking, we can dynamically keep the object of interest sharply imaged.
The human eye sees about 20 stops of dynamic range. A smartphone captures only 12, so in tough lighting, it renders either the bright windows or the dark interior, never both. We introduce Lucky HDR. Inspired by Lucky imaging and astronomy, our insight is simple. In every region, a few captured pixels are already well exposed. Instead of hallucinating pixels like prior networks, Lucky HDR selects and merges these real, lucky pixels from a handheld bracketed burst. Starting at the shortest exposure, it iteratively aligns and fuses each longer frame. Lightweight networks predict shift maps to align each target, then per pixel weights, keeping highlights from the base, recovering shadows from the target, and rejecting misaligned regions that cause ghosting. One shared model handles any number of frames. Trained entirely on synthetic bursts, Lucky HDR generalizes zero-shot to real smartphone captures, reaching state-of-the-art quality while staying small and fast enough to run on a phone.
We present a lensless approach for autonomous aerial navigation in complete darkness. Instead of a conventional lens, we place a piece of transparent tape directly on the image sensor. This simple optical element passively suppresses the background while preserving nearby obstacles, naturally generating ordinal depth cues for navigation. When an obstacle is detected, we reconstruct the scene using just a single iteration of an ADMM solver and use the recovered structure for obstacle avoidance. To minimize computation, we also develop a lightweight detector that operates directly on the raw, lensless images, triggering reconstruction only when necessary. The result is a compact, low-cost, and computationally efficient perception system for palm-sized aerial robots. We demonstrate reliable navigation through challenging indoor and outdoor environments with obstacles of varying shapes, materials, and textures. We hope this work inspires new directions in lightweight, compute-efficient robot autonomy. Thank you for watching.
In ill-posed imaging inverse problems, the choice of prior has significant impact on the reconstruction. We usually don't know the true prior, and an incorrect prior can hallucinate features that do not actually exist. The Bayesian evidence provides a principled way to choose between candidate priors, as it tells us how likely each prior generated the observation itself. This can be applied to a wide range of imaging problems, from deblurring images of dogs to reconstructing images of black holes. Computing the evidence is challenging for diffusion-based priors, but we introduce an estimator, DIME, that overcomes this difficulty. DIME identifies the best diffusion prior within a discrete set of candidates. However, all candidate priors may still be mismatched to the true data distribution. Therefore, we also propose a method for adapting a diffusion prior by combining it with weaker general priors as a product of experts. And this balance can be tuned with a single measurement by computing the evidence. Come by our poster to learn more and to see what our method reveals about black hole physics.
This is D3S, a millimeter scale camera that captures accurate 3D depth in a single snapshot. Passive depth sensing has a trade-off problem. To see far, triangulation needs a large baseline or focal length. That's why depth cameras are bricks. We broke that. One snapshot gives two views with different focus, and one closed-form equation turns them into sparse metric depths. The theory covers every optical parameter: focus, aperture size, sensor distance, baseline, and position. And the depth is selected where our consensus theory agrees. The quantitative result shows that 1 cm accuracy is from 0.3 meter to 1.6 meter, a wider working range than stereo cameras 10 times our size. For more detail, please scan the QR code or stop by my poster session. I'm happy to introduce my work with you.
We present VisionSim, a physically grounded simulation platform capable of simulating many different sensor types. It provides the user with raw sensor measurements and fine-grained control over sensing parameters. For instance, for thermal cameras, we can change the camera's thermal inertia, or we can also change material and scene properties, such as the sun's location. For direct time of flight, we also have access to many parameters, such as the system's overall power envelope, its temporal and spatial resolution, as well as its dead time, impulse response, and so forth. Similarly, for indirect or continuous wave time flight system, we can vary their frequency, the type of modulation function, and other key parameters. Of course, a rich set of pixel-perfect and temporally synchronized ground truth annotations are also available.
Controlling light with sound. a way to use sound waves in place of traditional optical components. When light enters water, it just travels straight, which is not something very interesting, at least as of now. But when sound is played in water, it creates pressure change leading to continuously varying refractive index field. In 3D, the field would look something like this. But when you pass light through it, this is where things get interesting. Instead of going straight like an unperturbed media, light curves and creates a line profile and propagates at the speed of sound in water. We exploited this physics to create high-speed projectors, which are 1,000 times faster than the existing systems, and were able to scan high-speed moving objects at 1,000 depth frames a second. Using the same physics, we also created an underwater light communication device, which can transmit data at 1,000 times faster speeds, just by playing sound on light. Check out our demos for more information. Till then, play sound to control light.
In this work, we used light fields and event cameras to realize the first system to image through turbulence for fast-moving non-rigid objects. Light fields independently capture views from subapertures, resulting in an array of event streams. The key idea is that each view shows the same scene but is corrupted by different turbulence. By combining the multi-view captures with the neural network, we can reconstruct stable video from the event stream. Further, by using the event camera instead of the traditional sensor, we are able to capture high-speed motion. Although our method is trained in simulation, it still generalizes to unseen non-rigid objects. It supports frame rate as high as 12,000 fps. Come and see our demo outside the Frick Chemistry Laboratory after this session.